All right, so page 12. Just to recap what we did for number 6, we talked about how if we want to apply power rule, we have to make sure every term is set up and ready for power rule. So a lot of times we can't jump directly into the calculus portion, right? We have to spend the time to algebraically do our cleanup. So radicals to rationals, we have to push all the denominator variable to the top, and then we can do power rule, and then we do additional cleanup after we find our antiderivative, plus c shows up, and then any negative exponent, we bring it back down to the denominator. Okay. Now, number 7 are trig integrals, but I want us to basically know how to use the derivative rules for trig and work backwards from those rules. So let's spend some time just see if we can recall each of our 6 derivative rules, because that's the strategy that I want you guys to take on the quiz tomorrow and also on future tests and AP exam. That when you get to your noun calculator section on your AP exam, you just write down the 6 trig derivative rules at the top of the page. And even though it looks like 6 rules, it's really 12 rules because all the integral rules are also can be found using those 6 rules. Okay, so let's spend some time here, see if we can recall.
How long is this one?
It's the length of these quiz reviews, front and back. Yep, tomorrow you'll use your calculator. I will give you I'll give you the width formula. I'll give you the limit, area definition of limit. I'll give you the summation formulas. But I'm going to ask you to memorize trig derivatives, memorize power rule, and also memorize trapezoid area. Okay, but I'll give you everything else. Okay, let's make sure that we can recall these rules here. Spend some time, see if you can fill those out. Okay, everybody good with the original 6 trig derivative rules? Okay, so now if we're doing the antiderivative, we're really just going to find whatever term is given to us. We're going to find it on the right side of the formula. And we know the antiderivative is just moving our way to the left side of the derivative rules. Okay, so let's set number 7 up. Antiderivative of all 3 expressions. All right, integral of -2 cosine x. Let's find cosine. What's the integral of cosine? Yeah, you're going to find the rule on the right side of your derivative, and you're going to work backwards. So cosine's antiderivative must bring us up to sine. Now the -2 is going to stay along with it. Okay. What about sine's antiderivative? Negative cosine, right? So you find sine on the right side of your derivative rule. You found it, but the negative has to be accounted for. It's going to have to stick with that cosine.
The +5 is for the
Yes, but eventually it will turn to a -5. I just haven't cleaned it up yet, but if you want to jump to just making it -5 cosine x, that works too. I just want to just show every step. Okay, what about cosecant cotangent? Yeah, so careful, right? The cosecant cotangent, we got to take care of that negative somehow. So the negative is going to have to stick with the antiderivative. But we are going to get those two negatives to cancel out. Okay, so I just want to make sure that are we comfortable reading the derivative rules and knowing how to work backwards to get those antiderivative rules. Okay, no need to memorize these rules, just know how to read it from your derivative rules. Okay, but I am going to ask you to memorize them or rememorize your derivative rules so that you can get into the habit of understanding, okay, if I have these 6 rules down, I really have 12 rules in front of me. Okay, now let's do our cleanup.
There's only one trig rule.
Mm-hmm. Okay, let's try number 8. Number 8, you're going to be finding the general expression. So what that means is you're going to take the antiderivative twice, right? F double prime's antiderivative will bring us up to F prime. Antiderivative again will bring us up to F of x. Along the way, a plus C will show up. Another plus C sub 2 will show up, right? Each time you find the antiderivative, a plus C is going to show up along the way. All right, so let's see if we can start number 8. Anybody still need to look at number 7? Okay. Okay. Number 8, I'm just going to start by indicating what I'm going to do. If I take the antiderivative, it'll bring me up to F prime. And as soon as I produce that notation, I can apply that calculus step. Now, the nice thing about this expression is everything is set up for power rule, right? There's no adjustment needed, no radicals to convert, no denominator variable to move, no parentheses to resolve. So I'm just setting it up saying, okay, I'm trying to move my way to F prime. If I take the antiderivative of that expression, the result of that expression, the result of that process will give me F prime. And now my next step is I'm just going to take the antiderivative. As soon as you apply your power rule, your integral notation goes away, your dx notation goes away, and the plus c will take its place. Okay, so we go through power rule. Every term rises by a degree of 1. What happens to that minus 6? Minus 6x. Okay, make sure that doesn't go to 0. That 6 will stay, and x will also appear. Okay, there's f prime. And there's my cleaned up version of f prime. So I'm halfway there. Okay. Questions up to f prime. Okay. I'm going to set up my integral process. Indicating what I'm going to do, I'm going to put integral notations around my f prime. And I know that process will take me up to f of x. So I'm just indicating, okay, if I take the integral of this, the resulting process will bring me up to f of x. Every term is still set up for power rule, so we jump directly into our calculus.
Can you skip the indicating step on please?
Hmm?
Can you skip the indicating step?
Yeah, I want to see the integral notation, right? Because I want you to see the habit of understanding what that means and also writing it out.
We only put it with our final answer. Like that'd be okay if you want us to also like put it with our work.
Which part? What do you
The
mean?
integral notation.
The integral notation is not going to be part of your final answer, right? Because your final answer will just be an expression, right? But your integral process will show me that what the process that you're taking. Yeah, the integral notation won't show up in your final answer because in place of it, you're going to have a plus c or multiple c's. Okay, so we go through power rule. What is c going to become? And then as we go through the antiderivative process again, another constant will show up. Either call it plus c sub 2 or call it plus k. Either way is fine. All right, any questions with number 8?
How do you determine how many C's?
So we're trying to get from f double prime to f of x. So that tells us that we have to go through integral process twice. Each time we go through integral process, a plus c will show up. So because we have to take the integral twice, we're going to have 2 plus c's.
So one's going to be CX.
Yeah, one's going to be cx and the other one's going to be plus k or c sub 2.
So that's just a sum. So this means like the second C.
That's right, second c.
Okay.
Or if you want to say plus k, you can do that as well. Those are the most common notations for a second constant that shows up, just so that we can differentiate between the first constant from the previous integral.
But we can't combine them.
We can't combine it because these are c values from 2 different layers, right? They're not from the same interval. But technically, every term is producing a plus c, so we are merging them within the same integral process. We're just not merging them across different integral processes. Okay, number 9, find the specific expression.
You have to do the integral.
That's right. Here, it's only asking for you to find the integral once. We're just going to follow whatever it says. We're going to take the integral of g of x, and the resulting process will bring us up to f of x. Now, when you see a specific expression problem, you're always going to arrive at your general equation before you can get to the specific, right? You've got to get that plus c to show up before you can work to replace that plus c. Okay, so I'm setting up my integral. Go through power rule. Clean up. Now you're staring at your general solution. Okay. To get from general to specific, we take the order pair that the problem provides, replace the x and y with those numeric values, and then try to solve for C. Make sure, though, that when you solve for C, that you just don't end the problem and say C equals whatever value. That you're going back and you're rewriting your general equation, and then you're updating that C with that numeric value that you found. Okay. Plug 2 in for y, plug -1 in for x. Combine like terms, clean up. You should get C equals 5. But then you're going back and you're rewriting the equation. This is my specific equation. Okay, any questions? 8 or 9? Okay, let's go to the top of the page and see if we can try the limit definition problem. Okay, does anybody still need to look at 9? Okay, here is number 5. Okay, I'm just going to rename that g of x, f of x, just so I can make it easier to line up with everything that we have in our formula. Okay, so given that the region is bounded by 6 minus x squared and the x-axis, there's x equals -1, x equals 2, so that tells you your a and b values. Use limit definition to find the exact area of the region. So here's the limit definition. I'll provide this for you on the quiz. So now your first step is replacing your a and b values with -1 and 2. Okay, so go ahead and try that first. Okay, so your a is -1, your b is 2. Basically, I'm going through and finding that width formula, which is 3/n, and I'm inserting them in their appropriate places. So this is where we should be before we get that height component out of function notation. Okay, any questions up to this point? Yeah, the 3/n is going to replace your b minus a over n in 2 spots. One for the width and once within the height component. Okay, so now we have to get this out of function notation, and the 6 minus x squared is going to help us do that. Okay, but I want you to spend the time to rewrite your function with spaces that are reserved for your upcoming expression to substitute, right? Your argument value. So we're going to go ahead and rewrite your function, but then leave a space wherever you see an x, right? So you're going to start off writing it as f of parentheses equals 6 minus parentheses squared. I think it's a really helpful step because if you can write it this form, then you're not going to make a mistake because you know exactly where your argument is going to go, right? It's going to go inside those reserved spaces that you created with your parentheses. Eventually, they will be taken care of with the summation formula. But for now, we're going to hold on to the I. Okay. All right. So your argument value is -1 plus 3 over ni. Oh, sorry. Thanks. Once you have those parentheses set aside, replace the parentheses with -1 plus 3 over ni. And now you can get that function notation out of the way and something that is going to be able to be combinable with that 3 over n. Okay. And then rewrite your expression, and now it's just a matter of doing algebraic cleanup. All right. Any questions up to this point here? All right, so the way you want to clean this up is you basically want to work inside out. So you want to FOIL this first. Once you FOIL that out, leave the parentheses there because you're going to have to distribute the negative through. Once the negative distributes through, the parentheses can drop out. Then you can merge with the 6 with combined like terms to the 6. And then after everything within the bracket is taken care of, then you can multiply the 3 over n through because you got to involve the width component of your area. Okay, so first things first, let's FOIL out those parentheses. Make sure that you're not just distributing the exponent through. You're going to miss some terms if you do that. Write it out twice and spend the time to FOIL. Hi.
So sorry to interrupt. Is camera here?
Camera.
Yeah.
Is it camera?
Yeah.
Are you camera?
Yeah.
Okay, well, I'm sorry, I don't know all of you guys. Happy birthday.
Thank you.
Your birthday today, right?
Yeah.
Okay, well, happy birthday. I hope I didn't interrupt you guys. All right, have a good day.
Happy birthday, Cam. Okay, FOIL. Now, once you FOIL, you still want to leave this in the set of parentheses because we don't want to forget about that negative, right? So distribute that negative through. And once that negative distributes through, I can begin working in that 6, right? That's 6 minus 1. Six minus 1 is 5. And now don't forget about that width component, right? You got to distribute that 3 over n through as well. Okay, any questions, any step along the way? All right, so now that we have every term all cleared up, now we can involve the summation, right? And then once you get that summation, notation, as part of every term, we can push the coefficients out, and then we can work in those summation formulas. Okay, so summation formula, we have a summation 1 that's going to show up, summation I that will show up, and summation I squared, right? You just have to find them on your formula sheet and be able to pull them. Okay, so as I assign a summation notation to every term, I'm also pushing the coefficients out in front and isolating the parts that I want to replace. So I'm going to replace summation 1, I'll replace summation I, and I'll replace summation I squared. But all those coefficients out in front will just tag along to whatever comes afterwards. Any questions here? Here. So summation 1 gets replaced with n. Summation I is n times n plus 1 over 2. Summation I squared is n times n plus 1 times 2n plus 1 all over 6. So now we're going to try to clean things up a bit more. Our goal is to find matching degrees because we're doing limit as n approaches infinity. If I can get matching degrees, then I only care about the fractional value that sits in front, right? The ratio of the coefficients. Now this last term feels a little messy, right? A lot of foiling out, but we can do a little bit of a shortcut in the sense that we know that there's multiple terms that's produced out of that, but only the first term with the highest degree is the one we care about. So just worry about multiplying the 27, the n, and 2n, and that's all we need, because that's enough to help us get that ratio we need with a matching with the denominator. Okay, so 15n over n, we just get 15 times n over n, we have that, which will produce 15 over 1. 18n squared plus 18n all over 2n squared. We see matching degrees. We know that will produce a coefficient that we need. And the third fraction, the 27, the n, and 2n will give us 54n cubed. There are more terms with lower degrees, but we know those will drop out. That's all we need, 54 over 6. So we're left with 15 plus 18 over 2 minus 54 over 6. We get 15, and 15 represents the exact area of that shaded region. Okay, questions?
We did the n cube on like the 6n.
Oh, how do we get the n cubed here?
Yeah.
The way that we got that n cubed was because it came from the previous term. Let's see. So you had 9 over n squared, I squared, but when you multiply it with 3 over n with that width, it should produce 27 over n cubed.
So was that squared from the 6 minus the x squared from like the original function? Is that also part of the n?
Yeah, so here, when I multiply 3i over n times 3i over n, the 3 times 3 is 9, the I times I is I squared, the n times n is n squared. But the middle terms, we only add. When we add the middle terms, the denominator is not going to change. Yeah. Yeah, all these little things that can throw us off, so good you're asking those questions. All right. Any other questions? Okay, let's turn to worksheet 2. This is page 13. All right, just want to kind of walk through what to expect on the quiz. Okay, be the same length as these worksheets. You're going to get a problem where you're asked to find the sum. It's only going to be a few terms, so there's no need to use summation formula. You're just going to plug in one value at a time, starting with the lower bound, and then keep adding the next term until you reach that upper bound of whatever is provided, right? So it's only going to be a few terms that you have to add together. Okay. Number 2, you have to write summation notation. So this is a sum that is half written out. We have to get it down to a summation rule. Yes?
Is it always going to start with 1, or if you have our first term, be like 3 or 4 for those?
Yeah, it'll always start with 1. Yeah, and now I think when we have time at the end, we can go through this problem. Okay. All right, number 3, you're going to have to use the width formula, right? B minus A over N, get your width, and then build your subinterval starting from the left endpoint. Keep adding to the previous subinterval, and then once you get all your width, or your width subintervals, then find the height component. If it's left rectangle or right rectangle, we can just stop with each of the subintervals that we've created. But if it's midpoint, then we have to do additional work of finding the average between each of the subintervals, finding that midpoint, and then attach it to the graph. All right. I think we'll have time to go through this. Number 4, table of values. This is one we don't use B minus A over N, right? We have a very specific way of grabbing the width from our subintervals. We have to draw our bracket in a very specific way so that we don't get thrown off. Okay, so seems like yesterday you guys were pretty good with that, so hopefully we can have time to practice those as well. You'll see a limit definition problem, like how we just finished with. Back page. You'll see a trig problem. Integral, we did that at the beginning of class. Power rule problem. Power rule problem. General expression, where we're going to get a plus c and plus k, depending on how many times you got to find the integral. And then a specific equation, we just got done with that, right? Find the general equation and then update the c value with a numeric value once you plug in your order pairs. Okay, I'd like for us to get some more additional practice with power rule. I want to make sure that we're really good with those. So, and also with integral of trig. So let's start with number 6 on page 14. All right. Recall your derivative rules. Set up your integral notation. And then each term, you're just going to find the rule that applies. Now, the last term is not a trig, right? Last term is power rule, so you'll do power rule for that last term. But the first 3 will be trig. Yeah, rewrite this for the function and show me the integral notation. And it's also good to rewrite because that last term you want to rewrite as x to the 1/2, right? Get that radical to show power rule form. First three terms, just find the rule, apply that, and the last term, power rule. Cosine becomes sine, sine becomes negative cosine, cosecant cotangent becomes negative cosecant. Okay, the last one. That 3/2 is showing up in the numerator and denominator, and the exponent and the denominator. I'm going to flip that 3/2 as 2/3. So 3 times 2/3 will just give me 2 because the 3's cancel out. Right. Yes.
What's the difference between the antiderivative and the ground? Just the amount of time that's good?
It's the same. It's the same. General antiderivative is the same thing as general solution. Yeah. Okay, are we good with number 6? Guys, number 7, can you add one more term to that problem just to get that additional practice? So add a term to number 7. There are 3 terms showing, but can you also include -3 over square root of x to the 5th? Okay, so number 7, add that 4th term before you apply power, before you apply number 1. Yes. Yeah, so we have to figure out a pattern for this, right? So this is, we know that anything that's changing has to involve I. So this is the 2I for the top. The bottom, these are all perfect squares. So this is I squared, 2 squared, 3 squared, 4 squared. So bottom's going to be I squared.
So if it's 2, I still got one right now. Oh, then that's just the end of it. So 5 stays. Okay.
5 stays minus stays, square stays, division stays. It's just
So we should define the power numerator and that's right. Okay.
Okay, number 7, make sure that you're spending the time to clean each term up. Now, that 3rd term looks a little strange, right? What is this?
Yeah.
Right. Do you see any variables here? E is not a variable. So this is a what? Constant, right? What's the integral of a constant?
Add x.
Just add x, yep. Right, it's just a messy constant. So if it's a messy constant, we treat it the same way that we do like a 2 or 3 or 5. We just make it rise to a degree 1. Okay. So you're not going to bring the e up to the top and do power rule e to the 5th over 5, right? E is not a variable, so you only do power rule for variables, for variable x. Okay. And also another thing, I want to make sure that I added this last term because I wanted to make sure that we know how to convert this. What's square root of x to the 5th? That's what a lot of people say, but it's actually what? 5 over 2. Yeah. Eventually, yeah, it'll have to come up to the top as negative. But the mistake that students make is thinking that that's a 1 here, but that's actually a 2. Or reading it as 1/5 or 2/5, but it's 5 over 2, right? This is the one that I see the most mistakes with in terms of converting from radical to rational. I think everything else is good. Just this is the type that it gives students most trouble. Okay. So rewrite each of your terms. And here is the step before power rule gets applied. 2/3 x to the negative 1/5, 3x squared, the third term doesn't change, and then 3x to the negative 5/2. Okay, so now we're ready for power rule. We add 1 to the exponent. I put a +5/5 and +2/2 just to show how I'm going to add 1 to each of those exponents. So my first term is going to show 4/5 and 4/5. Last term will show negative 3/2, negative 3/2. Okay, so here's my cleaned up version. Well, the 5/6 came from the fact that I reduced this 10/12 reduced to be 5/6, or you can just cancel the 2 and 4 out and make it 1/3 times 5/2, which is 5/6. Yeah, I skipped a step. You can multiply the two fractions together and then reduce it. Okay, any questions with 7?
I know no negative exponents, but are fractional exponents okay, or do you want us to convert those into those?
Either way is fine. You can get this in as radical form. That's fine.
Okay,
There's no negative exponent.
but it's not necessary, you can leave it as.
Yeah, you can leave it in either form, either square root of x cubed for that last one, or x to the 3/2. Okay, number 8 is also power rule, but there's a different way of cleaning this up, right? So number 8, spend the time. You see there are multiple terms in the numerator, but there's only one term in the denominator. Eventually the denominator has come up, but that x is going to influence every term up top. So just spend the time to separate each fraction. Create 3 separate fractions, each fraction with an x in the denominator. And once you get 3 fractions separated, you know that those are all now independent terms. Just clean everything up. Bring the x to the numerator, merge with the exponent above, or the variable above, and then get it ready for power rule. Okay, so cleanup is still needed for 8, but just looks a little different because we have to let each fraction take on an x. Okay, so here's my first step. Rewriting all the numerator with rational exponents, and then letting that x be a part of every denominator fraction. Okay. After you do this, then you can move the x up top.
But we can't do it first.
Yeah, well, you can, but I see a lot of students make mistakes because I see students move the x up to the top and they just merge with the last term and they forget to merge with the first 2.
Oh, because it's in more.
Because you have to distribute through.
So
So-
it isn't a negative exponent? Like, what did it offer you x to the negative 1?
It would be, but what I see students do is they bring x to the -1 up here, and they only remember to multiply this last term, and they completely forget to multiply the x to -1 to the first two terms.
Okay.
If you make it fractions, wouldn't the first term cancel out one of the x and 2x squared?
Yeah, this will become 2x squared. Yeah, this is just the initial step. We haven't done the cleanup, so you are going to clean up. And then after I saw that students had trouble remembering to distribute, I'm just going to tell students, right, you just separate every individual fraction, then you're not going to forget that the x is going to be part of every numerator term. Okay, so from here, you can either subtract the exponents, or you can bring the x up to the top, make it x to the -1, and then add exponents, right? Either way, you're going to be able to get the denominator cleaned up. And now, this is the place we need to be before we begin our power rule or calculus step, right? Every term needs to be nicely cleaned up, no parentheses, no radicals, no variable in the denominator. So now we can do power rule, right? X cubed over 3, we got to add 2 over 2, and then we got to add 4 over 4. Guys, real quick, can we do number 2 on the previous page here? Use sigma notation. You know the first one is I equals 1, I equals 2, I equals 3, I equals 4. Your summation rule. You know you're starting at 1, you're ending at 4. Go ahead and copy out the parts that are not changing. The 5 isn't changing, the minus, the square root, that all is going to stay. This is 2i. What's the denominator? I squared. 1 squared, 2 squared, 3 squared, 4 squared. Okay, help session tomorrow. Bring your calculator. I'll send out a reminder this afternoon. Okay, thanks everyone. Thanks, everyone. Yay.
See you tomorrow.
Thank you.